Hello, my name is Keenan Davis, student number G00183-458, and this is my capstone project, the laser harp. The laser harp is an instrument that plays using laser diodes at the top and photoresistors at the bottom. The lasers and the photoresistors are both wired to an Arduino microcontroller using an Adafruit music shield. What the Adafruit music shield does is it takes the output analog signal from the photoresistors when the laser is broken and sends a MIDI signal out, and that converts it into what sounds like an actual harp. Some criteria that were in the proposal for this project were that it would be a smaller instrument than an actual size harp. As we can see here, the total size is much smaller than a full-size harp. Other criteria were that it would use laser diodes and photoresistors and that it would sound like an actual harp. So let's take a look at the device and see what we have on the inside. All right, let's take a look on the inside here at the electronics. If we open this panel right here, this is where everything is housed. I've got the main breadboard right here that all the connections are made on. Here's the speaker that I'm using. It's got an auxiliary input and power if it needs charged. Right now I've got this charged, so we don't need that. Here's our auxiliary cable. We've got a 9-volt battery that we're using to power the microcontroller. So this is our Arduino Mega that we're using as the microcontroller and is connected to an Adafruit music shield. The reason we went with the Arduino Mega is because of the number of analog inputs it has. I think most other analog inputs on Arduino are limited, I think 6 inputs. And since we have 8 analog inputs for this project, that's why we went with the Mega. It's got 16 analog inputs. So on the shield, we have our speaker left and right. We'll cover that in a little bit. And we have our auxiliary output. This is where the MIDI signal, once it goes through the code and sends a MIDI signal out, goes through the auxiliary, and it's gonna come over here to our speaker. So let's get all this powered up and we'll take a look what we got going on here. So here's the system powered up. We got all of our laser diodes at the top, photoresistors at the bottom. Yeah, so let's see, good. So if we look a little bit closer here, what I've got going on, this is not actually the photoresistor. This is light diffusing paper that I cut in a circle and then shaped into a cone. What this does is it makes it, we can see here, this is a great example. Since I had to drill the holes at the top, they're not perfect. They're pretty close. I used the drill press and I got it as square as possible, but it's still off just a little bit. What the light diffusing paper does, even though the laser's not directly on the photoresistor, it diffuses the light, dispersing it to where we get a nice even coat, even though it's not directly on it. And that makes it to where it still plays. So if we take a look at our breadboard, we can see what we got going on here. Like I said before, we got eight analog signals here, and they're not all on the shield. The analog bar on the Arduino, if you can see right here, it runs this whole length right here. So we're still getting, I think, 6 pins right here on the ribbon cable connected to header pins on the Adafruit shield, and we got 2 more. I set these 2 pins a little bit further over because I didn't know if it was going to rub the shield. So I just made sure I had a little bit of room to play with. Looking on the inside, if we look at our breadboard, we can see these 2 long columns. I've got those set to 5 volts and ground. 5 volts is the red, ground is the yellow. And if we trail, let's look at this one right here. If we look at this, our signal cable, it's right in the middle, ground, 5 volts. And if you look on the inside, we've got a 30 kilo ohm resistor here, signal cable, and the blue and yellow. Blue and yellow, you can see all through here. Those are all our photoresistors. Red and black obviously are the laser diodes. So what we've got blue, yellow resistor, signal cable in the middle, 5 volts top, ground bottom. This is making a voltage divider circuit. As I'll show you in the demonstration on the Arduino software, this at rest, when the light is not broken, I get an analog signal of about 925 on a scale from 0 to 1023. The scale 0 to 1023, what that means on the lower end, that's going to give us a digital 0 signal to the Arduino, or a 1023. The high end will be a 1 to the Arduino. How this is done, right here we've got at rest with a voltage divider is about 4.23 volts. And then if we block the signal, anytime you block the signal, we go down to about 1.25 volts. So the scale for Arduino software is 3.5 volts or higher is considered a high or a 1, and 1.5 volts or lower is considered a 0 or a low. So, and we'll go over that in the Arduino software, what all that means, how it translates. In there, we'll use a serial monitor to actually monitor the voltage in real time and take some measurements to verify these claims. Covering the plan versus actual, there were two things that I had originally planned to do in the design that ended up changing. One of them was the speaker. So we're using a speaker here with the auxiliary cable for this demonstration because it has a built-in amplifier. If we look at the Adafruit shield, this bank right here, this is actually the amplifier bank, but what I found out, I didn't realize until I actually hooked up the smaller speakers I was planning to use. These are 8 ohm 2 watt speakers, is that they're not loud enough to pick up on the recording. And this was something I had changed last minute. If we hook it up, I'm just touching the top terminals up here. Let's see if we got it. I don't know if it was picking up or not, but it's so low that it's just not audible for the phone to pick it up. So it still plays through the speaker, but because this has, like I said, a built-in amplifier, when we hook up the auxiliary cable from the Adafruit, it's much louder. The improvement that could be made there is if I was able to implement a potentiometer into that bank or somewhere where that signal is going out. I could add a volume knob to increase the volume, but that wasn't in the original plan, and I didn't realize that until I had gotten the MIDI signal to work coming out of the Adafruit. Another thing that was proposed that ended up changing was the transistors in the circuit. Originally, I was planning to use transistors for the laser diodes, but the more I researched it, the more I found it was kind of useless to put it in there. When I was looking at the project initially, I was reading stuff about signaling transistors, how they may be implemented for the signal itself, and actually tying the laser diodes to the digital portion, the digital input of the Arduino. But the more I looked at it and the more research I did for this design, the scale that it's at, it just simply wasn't needed. There was no reason to add the transistors because it was doing nothing but adding a little bit of redundancy. So that was another thing that was changed. Another thing that I was successful in doing that was in my claim was that we got a full C scale that is in tune. It's within the A44 standard. That is the orchestra tune standard. That's what all the orchestras will tune to, is the A above middle C on a piano, which is 440 hertz. So this is indeed in tune with that. And we've got the full C scale as claimed in the paperwork initially. And that pretty much concludes our presentation. Thank you.